In this lecture, we will look at some special types of matrices. Remember that a matrix is a rectangular array of numbers. It has a number of rows and it has a number of columns. If the dimension is n by m, it has n rows and m columns. And the particular elements in the matrix are denoted by ai, j, where this is row I and this is column j. Now it may happen, of course, that I have exactly the same number of rows as I have columns. For obvious reasons, the matrix is then said to be a square matrix. M is the same as n and the dimension becomes n by n. And we need only one number to represent the dimension of square matrices. In some cases, when we are lazy, we may just use dots to represent numbers in a matrix. So each dot represents a number, which means that this is a square 3 by 3 matrix, while B being equal to dot 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 like this has 4 columns and 3 rows, so it's 3 by 4, and that is not a square matrix. A nice feature of the square matrix is that we can clearly define a diagonal. And a diagonal is this part here, the one that goes from the top left to the bottom right. This is called the diagonal of the matrix. The other possibility, going from the top right to the bottom left, is not called a diagonal. Also, we only use this notation for square matrices. For matrices that are not square, we cannot really talk about a diagonal. For example, in the B matrix, beginning at the top left, we could identify this with the diagonal, but then we wouldn't end up at the bottom right, so that's not called a diagonal. Neither is the second possibility, this part here. So it's only square matrices that have diagonals. The elements that are on the diagonal are called diagonal elements, while all the elements that are not on the diagonal are called off-diagonal elements. For example, here is a square 3 by 3 matrix. The diagonal is this here, and the diagonal elements are the elements 1, 4, and 5, while the other 6 elements are off-diagonal elements. In general, a square n by n matrix has precisely n diagonal elements. We also see that for the diagonal elements, for example, the first one is A11, that's the first diagonal element. The second diagonal element is in row 2, column 2. And the final diagonal element is in row 3, column 3, it's 5. So we can see that for diagonal elements, the row index and the column index is always the same. And that's why we can denote the diagonal element by ai. I goes from 1 to n. And whenever a and j are different in this notation, then we're dealing with an off-diagonal element. Here's another example. A is 2 by 2, therefore a square matrix. It's square, so we can define the diagonal, and the diagonal consists of the diagonal elements 1 and 2, while the other two elements, -1 and -2, are off-diagonal elements. So keep in mind, in matrix algebra, the diagonal is only the one that goes from the top left to the bottom right. Now, an interesting type of matrix is a matrix which has only non-zero diagonal elements. Such a matrix is called a diagonal matrix. That is, for a matrix to be diagonal, it must be, first of all, square. Second of all the off-diagonal elements must be zero. So here is an example of a diagonal matrix. It's square. The only non-zero elements are on the diagonal. Every element of the diagonal is equal to zero, so it's diagonal. And here is another simpler example of a diagonal matrix, a 2 by 2 square matrix with all the off-diagonal elements equal to 0. A very important type of diagonal matrix is the identity matrix. So the identity matrix is a square matrix. It's a diagonal matrix, that is, all the off-diagonal elements are 0 and all the diagonal elements are equal to 1. So we use this notation aij equal to, followed by this conditional definition parenthesis, 1 if the indices are the same, that is, if we are on the diagonal, and it's equal to 0 if the indices are different, that is, we're off the diagonal. The identity matrix is denoted by I, or sometimes when it's important for us to note the dimension of the identity matrix, we put the number of rows as a subscript. Of course, we don't have to put the number of columns because that's the same as the number of rows. So here is an example of I3, the 3 by 3 identity matrix. As you can see, all the off-diagonal elements are 0 and all the diagonal elements are 1. Also make sure that the conditional definition given for ai, j above will give us the same result as I3 displayed. Another type of matrices, not as simple as the diagonal matrices, but still simpler than the general type of matrices, are upper and lower triangular matrices. Those also play an important role in matrix algebra. So remember, for a matrix to be diagonal, it must be square and only the diagonal elements are allowed to be non-zero. That of course means that all elements above the diagonal and below the diagonal must be 0. So we say that the matrix is upper triangular if all the elements below the diagonal are 0. The elements above the diagonal need not be 0. This is why it's called upper triangular, because it has stuff on the upper side of the matrix. Here is an example. A is 3 by 3 square. It's upper triangular because it has only non-zero elements on the diagonal and above the diagonal. All the elements below the diagonal are 0. The name is quite natural, since all the non-zero elements, they form a triangle in the upper part of the matrix. Similarly, a lower triangular matrix is a matrix where all the elements above the diagonal are 0. So here's an example of a lower triangular matrix. This guy has only stuff below the diagonal. Everything above it must be 0. And again, the non-zero elements form a triangle in the lower part of the matrix. Make sure that you buy the mathematical definition. That is, it's upper triangular if ai, j is 0 for all I greater than j. Keep in mind that A is the row, J is the column. So if A is greater than J, we're at an element whose row number is greater than its column number. Well, if the row number is greater than the column number, we must be below the diagonal. And the definition of upper triangular tells us that those elements must be 0. Similarly, for the lower triangular matrices, ai, j should be equal to 0 if I is less than j. Again, if I is less than j, then the row number is less than the column number. And if the column number is greater than the row number, we must be above the diagonal.